All right, let's continue with a paired sampled t-test. And a paired sampled t-test, you have the same units of observation and you compare like a certain indicator before a treatment and after a treatment. So here's an example of a paired t-test. So the pre-treatment and post-treatment shows 16 students' academic test scores. The pre-treatment consisted of students being free to choose their bedtime. The post-treatment consisted of a mandatory bedtime of 10 p.m. So the treatment was go to bed at 10 p.m. And now we wanted to see whether this has a statistically significant impact. And we do that once using a two-tail test and once a one-tail test. And then we also still construct a confidence interval for the difference between post and pre. So when it comes to a paired sampled t-test, a paired sample t-test is essentially similar to a simple t-test where we have one variable, but our single variable is essentially the difference between post and pre. So let me copy this one into Excel. So those are our 16 observations. Let's put them here. And so have to. So the first one was the pre, and the second one is the post. So I'll just keep it a little bit shorter. And in the first column we have the observation, and then I create a new column and I just calculate the difference. So I do post minus pre. And let me just give that the same format. So we calculate, we subtract from the post the pre. So it looks like that for the first student, the going to bed at 10 o'clock didn't serve him too well. But now let's do that for all the others. And yeah, we don't need here. So let's remove that middle. So no border. And now I need to copy this one quickly, and then maybe the last one. Okay. Okay, so now it looks nice. So for the second student, it seems it had a good effect, and also for the third and the fourth. And so it's a mixed bag. So what we try to do is we basically look at the mean, and then we work with the mean as our main statistic that we look at. Okay, so what is the mean difference? I call it mean difference. So the mean difference is the average of all those differences. And that average is 3. So it looks like that on average, going to bed at 10 o'clock has increased the class difference. And let's make that smaller. Let's also calculate now the sample standard deviation. Sample standard deviation. And that is equal to standard deviation dot s. And then we highlight everything from D2 to D17. So the sample difference, the sample standard deviation, I mean, is 6.419. So we have 16 observations, so now we have to look at the sampling distribution. And for that sampling distribution, we need the standard error. And you know that the standard error is the sample standard deviation over the square root of n. So we have 16 observations. So technically, we do the sample standard deviation divided by the square root of 16. And then we get 1.6. Okay, let's center that. So this is our statistics that we need to work with. And so now what we have is, in a two-tailed test, we hypothesize that the difference is 0. So that means we assume a sampling distribution where the mean is 0. Let me try it again. So we have a sampling distribution where we hypothesize that the difference between post and pre is 0. But then it turned out that we got a sample where the difference between post and pre, so post minus pre, the average was actually 3. And our sampling distribution has a standard error, so we hypothesize that the mean H0 is 0, and our standard error is 1.605. Okay, so when would we reject in a two-tailed test the null hypothesis? So here we have the grade, and then we have to convert it basically into t-statistics, and we need to identify the critical value. When would we reject? So here we have a t-distribution, and we know we have 15 degrees of freedom. So we have like a t-distribution, and what we need to find is the critical t where we would reject the null hypothesis at an alpha of 0.05. So we need to ask the question, at what critical t do we have in a two-tailed test 2.5% to the left? So this area would have to be 2.5, and that area would have to be 2.5%. So in order to find that, we can quickly ask Excel, and we call that T critical two-tailed test. And we would use the formula for that, which is equal to T dot inverse. Then the probability that we want is 0.025, because that will be the probability in one corner of the distribution, and in both corners it is 5%, and degrees of freedom we have 15. Okay, so now we get a critical t of negative 2.131. And what I will do is I'll just absolute that again. But let's first make that bigger. I still put an absolute around. So that we get rid of the negative. And basically what that tells you is that both to the left of negative 2.131 and to the right of 2.131 we have 5% probability mass. And that is what we call the rejection zone. So in other words, when it turns out that our test statistic of 3 turns out to be more than 2.131 standard errors above a hypothetical mean of 0, then if that is more, we will reject the null hypothesis because it will fall into the rejection zone. So what is that test statistic? So the T, I call it T test statistic. So now we have to ask, how far away is a sample mean of 3 that is drawn from a population with a hypothetical mean of 0. So we have to calculate the t-score, and that is equal to the 3 minus the hypothetical value of 0 divided by the standard error. And we have already calculated the standard error in cell D20, so I just click into this cell, and now I get a test statistic of basically 1.87. So let's give that all the same. So now we have a test statistic of 1.87, and we can see that this is actually inside the rejection zone, or it's not in the rejection zone, it's before the rejection zone. So this is 1.87. So which is not in the rejection zone. So what happened is we said we want to conduct a hypothesis test at an alpha of 5%. So what that means is we would reject the null hypothesis if our sample has less than a 5% probability of coming from a population with a hypothetical mean of 0. And then we would say, well, if that probability is less than 5%, well, it could be that there's really no difference between the post and the pre-treatment, but the probability seems to be so unlikely that I reject the null hypothesis. But I could have made a mistake, but in this case, I do not reject the null hypothesis, so I also don't have to really worry about having made a type 1 error. But if I rejected it, I could have made a mistake. So this test statistic is nevertheless quite important because we can now tell why do we fail to reject. So that is our conclusion. We fail to reject in the two-tailed test. And so why do we fail? Well, what's the probability of our test statistic? And that is what we call the p-value. So now in a two-tailed test, I would like to know what is actually the area to the right of 1.87. So then I can use the command t.dist. But now I say negative the 1.87, because I want the area to the right of 1.87, which is the same as the area to the left of 1.87, if we have 15 degrees of freedom, and I want it cumulatively. So you see there is now in one pocket 4%. But because we have a two-tail test, I still have to multiply that and imagine, well, the same may happen on the other side. So I still have to multiply that times 2. So in this case, we have a p-value, which is 8%, and that is greater than the alpha of 5%. And if you remember, we said the alpha is the risk that you are willing to take to reject the null hypothesis, even though it is true. But here in this two-tailed test, we get 8%, which is still above the critical value 5% at which we would reject. Okay, but let's see how things may change if we have a one-tail test. So now let's do a one-tail test, and let me just quickly erase here everything. And some of the information we already calculated we can keep, especially our test statistic. That will not change in a two-tail test. Okay, so now let's do a one-tail test. And so now we want to test the alternative, essentially, that the post minus pre had a positive effect. So we have our distribution now again. So we have our sampling distribution, and again we hypothesize that the mean is equal, or the hypothetical mean of that population is equal to 0. And then the standard error is also still the same, so the standard error is still 1.605. The only thing that has changed is now that we do a one-tail test at 5%. So we still have here our average of post minus pre, the average, which is equal to 3. And so now we have to do a one-tail test, and we need to look at the alpha in a t-distribution. So here we have post minus pre, and here we have again the t-score. And the distribution looks basically the same, but now we need to find the t, the critical t, where we have a rejection zone only in one direction. So we need to find the t which defines this rejection zone to the right. So what is this t? So let's call that t critical, but then in parentheses one tail. And then you see when we did the two-tail test, we took the 5% and split them up, or split it up into two pockets. So we look at only the t-score where we find to the left or to the right only 2.5%. But in a one-tail test, all the 5% is in one pocket. And so now we will say equals t dot inf, open parentheses. Now the probability is 0.05. How many degrees of freedom do we have? Well, we still have 15. And now we get the t. And you see, and let's absolute it again. So that is now only 1.73. Or 1.753. Okay. Well, let's make this so. So 1.753. So it is much closer to the mean. It's much more inside than the other one, because to the right we have more probability mass. So now this is our critical value, 1.753. We can barely read it, but that means so this. So this critical value is 1.753, but our t statistic, which is this one, well, now this is now in the rejection, so this is still the 1.87. So 1.87. So now our test statistic is in the rejection zone, and for a one-tail test, we would reject the null hypothesis that there is no difference. Then we would say that statistically highly plausible, and well, it would be, what we would say is that it is statistically significant at 5% that we reject the null. And so, but anyhow, so as you can see here, that this dashed line that cuts through 1.87, and that means we could have made a type 1 error. Well, there is still a chance in this one-tail test, and I'll make this now this red area, so everything to the right of this 1.87 t-score, so this red area here, that probability, that is the probability that we made a type 1 error. And so how big is this probability that we made a type 1 error? Well, this is then the p-value again, and specifically the p-value associated with the one-tail test. P-value one-tailed. So now what we do is we just use again t-dist, and I want to know what's the area to the right of 1.753. So this is the formula t.dist, but the area to the right of 1.753 is the same as the area to the left of negative 1.753. So I'll just put a negative sign in front, and then I click on the cell with the critical t of a one-tail, and then I say degrees of freedom 15 and cumulatively yes. And now this seems to be actually close to, oh, that's interesting, that's exactly, hold on, oh, I'm sorry. Of course, this is exactly 5%. I made a stupid mistake. I don't want to know the area to the right of 1.753. Well, that's obviously 5%, but I want the area to the right of 1.87. So I need to replace the cell with the test statistic and not the critical t. Okay, so now we get 4%, and that makes sense. So that means there is still a roughly 4% chance that we rejected the null hypothesis, even though it might be true. And I always like to use this example to really understand the nature of a hypothesis test. Let's say you were supposed to test whether a certain die is fair. And let's say you test it by rolling the die 100 times. Or let's just keep it easy. Let's say you assume that you want to roll a die 60 times. Well, then you would expect that on average you should expect 10 times a 6, because the probability of getting a 6 is 1 over 6. So if you roll the die 60 times, you should expect 10. Well, let's say you find that that die rolls one 6 after the other. Whenever you roll, a 6 comes up. Well, theoretically, it's plausible that, you know, the probability is 1 in a gazillion trillion, but it could be that you roll a die 60 times and every roll is a 6. It's not very likely, but theoretically, who knows? But you will say, if you have, let's say, a certain number of 6s which seem to be highly unlikely, like you say, well, if the number of 6s that I see in front of me when I roll a die 60 times, if that number of 6s has a probability of less than 5%, you decide to conclude, well, I don't think that this die is fair. So this is a little bit the nature of a hypothesis test. So in the first one, in the two-tail test, we failed to reject, but in the second one, in the one-tail test, we would reject. Okay, so there's also a question which asks for the 95% confidence interval. And for this, we can already rely on the T for the two-tail test. Because if you remember, when we did the two-tail test, let me first erase this here. So if you want to do the 95% confidence interval, we would say, okay, so we have a distribution. And we have our sample mean of 3. And then we build around that sample mean a 95% confidence interval. So that means in each pocket we have 2.5%. And we already know that the corresponding t statistic is 2.131. So then if we just apply again the formula for the confidence interval, we would say the 95% confidence interval, that is equal to our sample mean plus minus the t, where alpha half is 0.025, and we have degrees of freedom 15, times the standard error, and we already calculated that too, that's 1.65, 1.605, so times the standard error. Okay, so now let's do that quickly in Excel. So then we would say the lower limit is equal to our mean of 3 minus the critical t for a two-tail test, which is 2.131, times the standard error, which is 1.605, and then we would say that the lower limit is actually negative 0.42, and the upper limit would be equal to the difference of 3 plus the critical t for where we have 2.5% in each pocket times the standard error of 1.6. Okay, when you see the 95% confidence interval also includes again the hypothetical population mean. And that is of course closely related with the fact that in a two-tailed test we actually fail to reject the null. Okay, So anyhow, so I hope the concept is clear. And of course, the last thing what we want to do is we want to quickly tell Excel to conduct that paired sample 2 test for us. So in this case, we go to data, data analysis. And if you don't see data analysis, make sure that you pull it up from options. And then you go to add-ins, Excel add-ins, and make sure that the analysis toolpack is checked. Okay, so we go to data analysis, and now you see there is a t-test paired sample for means. Okay, and then it's pretty straightforward. So it's a moving average, so t-test to sample for means. So this is the one that we want, a paired t-test. And then we have to tell Excel what's the variable range 1. So we add the labels, because I will highlight now for variable 1. I start with the post. Actually, gotta be careful, the post is column C in my case. And the variable 2 range is B. And then I tell Excel to just put it maybe somewhere here in our sheet, maybe next to our calculation, maybe here. And then we just say OK. And maybe up here, it's maybe better. Okay, so now here we have the result. Okay, so now you see the post is 88, 85, and now let me limit everything to also 3 decimals. And then we can see our test statistic, the t-stat, is also given by Excel as 1.87. So that's the same. Then it says what's the probability in a one-tail test. We also calculated that here as 0.041. Then what is the critical t-score if you want to do a two-tail test? Well, the 2.131 we have here. Then what's the probability of a two-tail test? Well, that's the 8.1%, which you see here. So, and Excel also tells you the degrees of freedom, and by default, if you don't click anything, it tests whether the difference between post and pre is actually 0. Okay, so I hope that is clear. And so now you know what Excel is actually doing. And so just for the fun of it, let me delete this one again. What we also could have been doing, let me remove that here quickly. What we also could have been doing, we just use the difference between post minus pre, and then I create a fake column where I assume the null is always 0. So I just enter the 16 zeros, and then I can also do a paired t-test on those 2 columns. I get the same values. And that is what we did actually in the simple t-test if you want Excel to give you the results. So let's double check. Let's go to data. Again, t-test paired to sample. But now we take, we have a new variable range. So in this case, I'll do first the fake zeros. And then for variable 1, I do the post minus pre. And I have the output again at the same position. And then you see the post minus pre is 3, It also gives you the variance, the number of observation, degrees of freedom. But the most important thing is here we get again a critical test statistic, which is again the 1.87. We get again the one-tailed p, which is 4%, which is why we rejected. The critical one-tail statistic is 1.753. So it's technically the same thing. So, but anyhow, I hope you get now a very good feeling also for what Excel does. And let's stop here for now, and then let's go into 2 sample t-tests in the next video.